This is the second video in our introduction to the Lights Out game. In the first video, we looked at an introduction to how the game is played. In this video, we're going to start looking at strategies for actually winning the game and using that to prove theorems. So in this video, we're going to look at some elementary methods that I call button pushing strategies. These are just how do we push the buttons in order to win the game. So we're going to look at some ways to start with a very complicated lighting pattern at the beginning of the game and try to simplify that labeling so that it's easier to deal with. And then we're going to use those simplified, I call them standard forms, to help determine whether or not a lights out game can be won. So I want to first of all clear out some issues to make things a little bit easier for us to deal with, and I want to deal with the order of the toggling. So the question is, if I play the game twice where I push the buttons the same number of times each time, but I do so in a different order, is that going to affect my final labeling? Well, in order to understand that, imagine that you are a vertex on the graph and you have some initial label with an element of zk. Now, after the entire graph has been toggled, question is, what determines your final label as a single vertex? Well, certainly the number of times you're toggled is going to make a difference. Each time you get toggled, your label gets increased by 1. And yeah, that tickles. And also the number of times each of your neighbors is toggled, right? Each time your neighbor is toggled again, it increases by 1. And then your final label is going to be determined by the total of all of those toggles. Notice, however, that the order of the toggling does not affect you at all. The only thing that matters is how many times each vertex is toggled. So if you have a graph with some initial label, then the order of the toggling in the lights out game has no effect on that final labeling, which is really nice because now we can just concentrate on how many times do I have to toggle each vertex, not in which order that I have to do it. Now, for many classes of graphs, it is very helpful to toggle the vertices so that the labeling is in some standard form, right? So if you look at this is just a regular old path graph. If you look at this path graph, that lighting is a mess, right? You have like some of them are off, some of them are on, and it's very difficult to tell what a nice strategy is going to be. So what we're going to do is not so much concentrate on trying to win the game right now. We're going to put the labeling so that it's in a more manageable form. And the way that I'm going to do that is I'm going to start all the way to the, well, almost all the way to the right, to the second from the right, and keep toggling the vertices until the ones on the right are off. So I'm going to hit this one 3 times. So this set is, the labels are in Z4, so we have 4 colors. So I'm going to toggle this one 3 times. 1, 2, 3, and I don't care what's happening to the left, but notice on the right, I turned that one off. It's now at 0. Now I'm going to move over one more vertex. I'm going to hit that one twice to turn off the vertex that's to the right of it. 1, 2, and again, I don't care about that vertex or the one to the left of it. I'm just making sure I'm turning off the vertices to the right. I'm moving one more over to the left. I'm going to hit that one 3 times. 1, 2, 3. And once again, I don't care about that one. I don't care about its neighbor. All I care about is the ones on the right getting turned off. Now I move one more to the left. I hit that one once and everybody's off. And actually, that one's off too. So I'm going to not just move over one to the left now. I'm going to move all the way to the end, hit that one once. And now I have a labeling that is much more organized, right? Every vertex is off except for the one way on the left. And as you could probably see by a very simple induction proof, any labeling you have of the path graph can be toggled so that it ends up in this form. So our first proposition or lemma, depending on how you want to look at it, if you have any labeling pi from the vertices of the path graph to zk, then you can toggle those vertices in such a way that you obtain the labeling, I'll call it pi prime, where pi prime is equal to 0, but for every vertex except maybe the leftmost vertex, right? The leftmost vertex may be off, may be on, but that's the only one that has a possibility of being on. And that one is much nicer to try to figure out whether or not you can win, right? So the idea is to take your chaotic labeling, hit the vertices until you have this nice standard labeling, and then ask yourself whether or not you can win that labeling. If you can, then you can win. If you can't, then you can't win. So now I'm just going to look at this particular game. So all of them are off except the one on the left. The one on the left has labeling C. And by the way, the C could be 0, but it could not be, may not be 0. So I'm just going to leave it as C for right now. And then the way I'm going to figure out whether I can actually win the game is ask myself, okay, how many times am I going to hit that first vertex? I don't know, so I'm going to represent it with a variable. I'll call it X. And so my question is, what happens when I hit that first vertex X times, and then try to adjust X so that it turns off all the vertices, if possible, right? So when I do that, the leftmost one gets raised from C to X plus C. It gets increased by X, but also the one to the right of it gets increased by X as well, from 0 to X. Now, I can't hit that leftmost vertex anymore, and I got to ask myself, well, how many times will I hit the vertex next to it in order to win the game? What's my only possibility? Well, whatever I do, I have to make sure to turn off that vertex on the left, right? And since I can't hit the vertex on the left anymore, I've already hit it X times, that's the total number of times it gets toggled, the only way I can turn it off is by hitting the one just to the right of it. And I've got to do that in a way that takes it to 0. And there's only one way to do that. I've got to hit it K minus X minus C times. Remember, K is 0 in ZK. So if I hit it K minus X minus C times, that will turn the label on the left to K, which is the same as 0. But then it'll also affect the vertex that's second from the left and third from the left as well, just like that. So I get 0 on the left, and I get K minus C and K minus X minus C as well. Now, if I think about, okay, at the end, how do I make sure that K minus C gets turned off? Well, it can't be the one on the left. That one was tapped out at the beginning. It can't be the second from the left, because if I toggle that one, it's going to screw up the one on the left. So the only way I can turn that off is by toggling the one that's just to the right of that, the salmon one in there, that's K minus X minus C. And in order to do that, I have to hit it C times. When I hit it C times, that increases it from K minus C to K, and K is the same as 0. But again, that's going to affect these other ones as well. You're going to get this K minus X and C for the third and fourth vertices. But the first two are off, and I can't hit the first two anymore. And actually, I can't hit that third one anymore either, right? Because if I do, that's going to screw up the second one from the left. Which means that the only way I can turn off that K minus X vertex is by hitting this one. Oh my goodness, I got to hit that one X times. That looks very familiar. And when I hit that one X times, it turns that third one off. But now I'm in a very familiar situation. That looks exactly like the situation that I had when I first hit that one on the left X times. That one turned into X plus C. The one right next to it on the right turned into X. And so what you can kind of see, hopefully, and an induction proof will actually verify it, is that every time you go through this process, every 3 vertices, it's going to come back to exactly where you were before. So whatever you started with on the first one is going to end up in the same one on the fourth one, same one on the 7th one, the 10th one, etc. And to figure out how that happens, or to sort of describe that in a theorem, what we're going to get is, well, okay, so let's say for Pn, your initial labeling is pi of V1, that's your labeling for V1, is equal to C. That was our C, that was our yellow one at the beginning. And then pi of Vi is equal to 0 for all the I not equal to 1. We're going to let Di be the color of Vi after we finish toggling Vi. And when we do that, remember, when we hit the first one, V1, it turned it from C to X plus C. So after we hit V1, which is what we want, then we get X plus C, which tells us that, for instance, D1 is X plus C. By a nice little induction proof, we have 3 formulas for Di depending on where we are in that cycle. Remember, we cycle through every 3. So what the label is after we toggle that vertex depends on where we are mod 3. If we toggle a vertex like 0 mod 3, like 3, 6, V3, V6, V9, V12, etc., we're going to end up with K minus X. If we get to 1 mod 3, we get X plus C, right? And if we get after we toggle one that's 2 mod 3, it's like 2, 5, 8, etc., then we get k minus c. And so what we have to think about is, okay, how am I going to win this game? Well, it's going to depend on what happens after you toggle the last vertex. If you toggle the last vertex and it's off, then you win the game. And if it's not off, then you don't win the game. So if you notice in those first two formulas, the k minus x, the x plus c, if you wanted to, you can manipulate the x. Remember, you have control over x. That's how many times you hit that first vertex. You can manipulate the x so that you win the game. If you let x equals 0, if you end up on a multiple of 3, 0 mod 3, that says that if you hit x 0 times at the beginning and go through this process, you will end up with all of them 0 at the end as well. So that means you can win the game. And with that x plus c, that one looks a little bit intimidating, but it turns out if that x is k minus c, then you'll end up with 0 at the end, which means all the vertices will be 0, and then you win the game. Now that last one, that k minus c, is a little bit tricky, because notice that x is not in that formula, which means that no matter how many times we hit x at the beginning, we're always going to end up with k minus c. And if k minus c happens to be non-zero, then we're doomed. It means we can't win the game, right? So that says that if we're at 0 mod 3 or 1 mod 3, we can tweak x so that we can win the game, but if we're at 2 mod 3, we can't. Which says that the lights out game on the path graph Pn can always be 1 over zk precisely when n is congruent to 0 or 1 mod 3. Not 2 mod 3, because that one is out of our hands. So that's one way of using the button pushing method to give us a theorem. And we can do something similar for cycles. We're going to do exactly kind of the same thing, try to turn everything off as much as we can. So here we're going to turn this one off, right over there on the left. We're going to move down here and turn the one off the one to its left, and keep on going in that way. And then that's about as far as we can go, because if we start toggling the vertex with 1 on it, then the one to its left is going to turn on, and then we'll just sort of end up in this endless cycle. So the best we can do for standard form is to have all of them off except for 2 of them that are right next to each other. And so if we're in that situation, we can see how we can win the game. This one's going to be a little bit more tricky because it's going to depend on how many times we hit the first one. I'll call it x1. And notice that we hit it x1 times. That affects the one to its right, which we care about, but also to its left, which is a little bit confusing. And if we hit this one x2 times, that's going to affect both of those as well. After that, everything is determined, right? I'm going to hit this one in a way that turns the one off to its left, right? I'm going to hit this one in a way that turns off to its upper right, right? Then I'm going to hit this one to turn off the one to its right. And now I'm at the very end. I have no choice but to turn the one off to its lower right. And then I end up in this situation here. Very similarly, as we did for the path graphs, if we have an initial labeling where pi of v1 is equal to c1, pi of v2 is equal to c2, and the rest of them have labels 0, right? Again, we let di be the color of vi after we finish toggling. So we want all of those to be 0, except there's going to be a little twist at the end, right? So d1 is going to equal x1 plus c1, right? That's because we hit it at the very beginning. And d2 is going to be x1 plus x2 plus c2. We get very similar formulas for the di's using induction. Except we have to now be very careful about what happens at the end. Because what happens at the end at our vn is it's going to affect that vn minus 1 that comes right before it. But then it's also connected to the beginning, to v1. And we got to make sure it turns off that one as well. So here's what's going to happen at the very end. So the vn is the one on the left, the very left, the one that's kind of the pinkish one, right? And the one that's sort of like the cyan blue on the right, that is v1. And then that green one in the middle is vn. And we got to make sure that when we toggle vn, that we turn off itself, the vn, and both of the ones on the left and right. But the only way we can do that is if both of those on the left and right have the same color, right? So we need that, and what that, right? Because if they're not the same color, no matter how we toggle the green one of them is going to be off and one of them is going to be on, right? So we need that dn minus 1 to be the same as the one on the right, the x1 plus x2 plus c1. But also, remember, that green one at the very beginning was affected by v1. When v1 was hit x1 times, it turned vn the label xn, which means that we also want dn to be negative x1 to cancel that out. It's a little bit complicated, but that's how it goes. We're going to end up having to solve a system of 2 equations and 2 unknowns. We can do that. That's just regular old linear algebra, easy linear algebra. And when we do, it ends up that the cycle graph is always winnable over zk. In other words, we can always win the game precisely when n is congruent to 1 or 2 mod 3. And as it turns out, we got to be careful about how many colors we have, because if the number of colors happens to be a multiple of 3, then it's not always winnable. So we might be able to lose if we have a multiple of 3. So we also have to make sure that the GCD of 3 and k is equal to 1. So that gives you an idea about some of the button pushing methods that we're using. In the next video, we're going to talk about some linear algebra that reduces winning the game to solving a system of linear equations.